Hi everyone, welcome to the Statics Problem Set Answer Guide. The first question is asking you to describe the difference between work and torque. Well, work is done when a force is applied over a distance, say d, and that can be thought of with a very simple example of a block on a table. You have an applied force and it moves to a new location. We'll call that d. I don't know why I drew that d there. Alternatively, torque is a force multiplied by a moment arm. So say you have a force here and it's applied a distance from a joint center of rotation, for example, then you have this torque equals the force times the moment arm, both of which have units of Newton meters. In question 2a, we have someone who's holding a weight in their hand, and the weight is 100 newtons. So say this is a kettlebell or something like that, and the weight is a distance of 0.3 meters from the elbow joint center. So to calculate the torque, it's going to equal the force times the moment arm, which is 100 newtons times 0.3 meters, giving you 30 Newton meters. In question 2b, we have a slightly different scenario. This time, the forearm is elevated by 30 degrees above the horizontal, but it's still holding the 100 Newton weight. Looks like that. But now we need to calculate the perpendicular distance between the elbow joint center and where the hand is holding the weight. So we'll call that distance r dot. To calculate r dot, we take 0.3 meters, which is the distance along the hypotenuse between the elbow and the hand, and we multiply that by the cosine of the angle, which is 30 degrees, and we get 0.26 meters. So the resulting torque is then 0.26 meters times the force, which is 100 newtons, and we get 26 Newton meters. In question 2c, we're asked to calculate the muscle force that a muscle would need to generate to hold the hand and forearm at a position of 50 degrees above the horizontal. The hand is still holding a 100 Newton weight. So the first thing we want to do is we want to create our free body diagram. So we'll draw in this muscle, and that muscle is acting a distance from the elbow joint center. We'll call that RM for muscle moment arm, but there's also the moment arm due to the weight about the elbow joint center, and we call that R dot, the perpendicular distance between the hand and the elbow. So in this static position, the sum of the torques around the elbow equals 0. The torque due to the muscle is going to be positive because it's acting counterclockwise in this free body diagram, whereas the torque due to the weight is going to be negative because it's acting counterclockwise. So the torque due to the muscle is going to be Rm times Fm, or force due to the muscle, and that's positive. And then we subtract the torque due to the weight, which is going to be R dot times the force of the weight, and that's going to equal 0. Rm is given. Rm equals 0.03 meters, and we need to calculate R dot, similar to the previous question. So that's going to equal 0.3 meters, which is the length of the forearm, multiplied the cosine of the angle, which is 50 degrees, and that's going to give us the perpendicular distance between the weight and the elbow, and that's going to equal 0.193 meters. So then we can solve this equation for muscle force. So Fm is going to equal R dot times the force due to the weight divided by the muscle moment arm, Rm, and that's going to be 0.193 times 100 over 0.03, and that's going to give us 642 newtons. In question 3, we have the scenario where someone is doing leg exercises to strengthen their knee extensor muscles, and they're wearing a weight boot, and the weight boot weighs 150 newtons, and it acts a distance of 0.35 meters to the knee joint center. And now also in this problem we have the weight due to the mass of the shank and the foot as well, and that's going to be 40 newtons, and that distance between the center of mass and the knee joint center is going to be given by 0.2 meters. So in 3a we have the scenario where the shank is perpendicular to the ground. So the sum of the torque is going to equal the negative force due to the weight times the moment arm due to the weight minus the force of the leg times the moment arm of the leg, and those are both negative because they're acting counterclockwise about the knee joint center. And it's pretty clear to see in this question in 3a that the moment arm of the weight and the moment arm of the leg both equal 0 when the foot is in this orientation. So for 3a, the sum of the torque around the knee is going to equal 0. Okay, in question 3b, the shank is in a different position. So let's draw a free body diagram. This is the shank, and then this is the weight boot, and it's at a position of 20 degrees below the horizontal. The weight of the boot is acting downward here, and the weight of the shank is acting downward here. That's at the center of mass of the shank. This is force weight, this is force leg. And now let's draw in the moment arms of each of those forces. So this is going to be RL, and then this is going to be, that distance is going to be R weight, or RW. So now let's draw a torque equation. The sum of the torque is going to equal negative times the force due to the leg times the moment arm of the leg minus the force due to the weight boot times the moment arm of the weight boot, and those are negative because they're both acting counterclockwise going according to the right hand rule, so that's going to be a negative torque. And now we need to solve for the moment arm of the leg and the moment arm of the weight boot. First, the moment arm of the leg, that's going to equal the distance between the center of mass of the shank relative to the knee joint center, which is 0.2 meters, times the cosine of the angle, which is 20 degrees, and that's going to give us 0.19 meters. Now for the moment arm due to the weight boot, that equals 0.35 meters times the cosine of the angle, and that gives us 0.33 meters. So now if we write out the full equation, we have negative 40 newtons times 0.19 minus 150 times 0.33, and that equals the torque at the knee, and the final answer is negative 57.1 Newton meters. In the final question, in part 3c, we have the position of the leg in the same orientation. It's 20 degrees below the horizontal. But now we have a muscle, the quadriceps muscle, acting to oppose that net joint torque. So that quadricep muscle is going to generate a torque in this direction. It's going to be positive, and it's going to be opposing the torque due to the weight boot, and the torque due to the weight of the leg, so torque L. We'll finish this free body diagram by drawing the moment arms for each of those forces. So we have the force due to the leg, and that's going to be acting at a moment arm RL. And then finally the moment arm due to the weight, that's RW, just like in the last question. But now there's a new moment arm, call this RM, and it's acting a distance of, let's see, 0.025 meters from the knee joint center. The torque equation is going to be very similar to what it was in part 3b, except now we need to have the torque, we need to include the torque due to the muscle. So first we'll have negative force due to the weight of the leg times the moment arm of the leg minus the force due to the weight boot times the moment arm of the weight boot. But now we're going to add in the force due to the muscle times the moment arm of the muscle, and this is what we want to solve for. We can rearrange that equation, and it's going to look like this: FLRL plus FWRW divided by RM, and specifying or adding in those quantities from before, we have 40 times 0.19 plus 150 times 0.33 divided by the moment arm of the muscle, which is 0.025, and ultimately that is going to give us the force of the muscle, and that equals 2,284 newtons. And I forgot to mention that these quantities here, 0.19 and 0.33, those came from the calculation before, where we have the length of the center of mass of the shank relative to the knee joint center, which is 0.20 meters. That's going to be times the cosine of 20 degrees, 0.19, and then the moment arm due to the weight boot is going to be the same, 0.35 times the cosine of 20, giving us 0.33. So that should complete the problem.